experts. Today we're talking all about analog and power and have live sessions exploring power connectors, static protection, GaN for servers, and EMC optimized RS-485 and CAN buses. All Summit sessions will be available on demand, and each of our presenters also has a microsite loaded with more opportunities for skill building and professional development. We also have prizes. Get a giveaway entry each time you register for a live session for your chance to win some All About Circuit swag or a Pick It Yourself grand prize. And now it's time for today's keynote, brought to you by Breadboard. Breadboard is changing the way engineers design and source. Get 80% faster procurement, up to 20% lower cost, and bombs in minutes, not days, for fewer errors and faster launches. Don't get left behind. Start building smarter at breadboard.com. Today we're joined by John Koeter, Senior Vice President at Synopsys, and we're going to explore what it's going to take to build tomorrow's chips. That means that we're digging into the role of pre-verified IP blocks for modern chip design, what hyperscalers really want out of a chip because just the specs are not enough, and why chiplets and 3D silicon make thermals harder than ever to manage. John, thanks for being here. I've really been looking forward to this.
Thank you, Daniel. It's a pleasure being here on your show.
I'm curious, what gets you excited about tech today, and what got you excited about engineering originally?
You know, from the time I was a very small boy, I've loved science fiction. And if you want me to know what makes me really excited, is seeing those ideas from the 60s, 70s, early 80s turn into reality. And being a part of that journey. It's amazing. I remember the very first time I heard about the internet, an AI assistant, and a network classroom environment was in a book that I read in the late 70s. And now that's all kind of state of the art and coming true here later, 40 odd years later. And it's just so exciting to see these ideas and how they're going to change society and being part of that journey.
Are you still a sci-fi fan, and is there anything you're reading currently or in the last year or so that you're excited about that sets us up for 20 or 50 years from now?
Oh yeah, I am. I love science fiction, and right now, some of the things that I'm reading about is the effect of major technological shifts onto society. So things like, what if you have a neural implant? How does that change? What if you live to be 200? How does that change the basic institutions of our society? It's those kind of big picture ideas where technology meets society that really makes me interested.
And you're the SVP of IP, or intellectual property, at Synopsys. How much do you think intellectual property plays a role going forward versus a more traditional kind of engineering focused business that focused on gadgets or machines or hardware?
Well, you know, one of the biggest trends in the industry right now is the tremendous left shifting or acceleration of chips, and chips are underpinning all aspects of the technology revolution that we see ourselves in with AI. So, intellectual property or IP are pre designed blocks of silicon that go into a larger chip, often called an SoC or system on a chip, that then turn into a system that you would buy or use as a consumer. So these pre-designed, pre-verified, high-quality blocks of logic that go into these larger chips are an absolutely essential part of the whole way to accelerate chips faster. And then, you know, I'll give you some examples of these typical type of IP blocks, things that you deal with on a daily basis, things like USB, Ethernet, HDMI, PCI Express, various memory interfaces. These are things that you deal with on a daily basis as a consumer user. And so what we do is we provide those fundamental building blocks that our customers can take and put into a larger SoC.
You actually started your early days at Texas Instruments doing chips, and you got an electrical engineering degree from Cornell. Can you talk about what you learned during your early days of your career and of school, and how that has influenced what you do today?
Oh, sure, Daniel, be happy to. So I was incredibly fortunate when I worked at TI because TI at the time was one of the largest semiconductor chip suppliers in the world. But the division that I was in, which is the ASIC division, it was called, was kind of like a small startup. So I got to wear many different hats. I got to go onto the test floor. I got to do layout. I got to interact with our customers in an engineering application and an AE application. I got to define new products and new market opportunities. I get to look at, important trends in the market. All of those things provided such a broad background for me that I really think is fundamental to the success that I've had in the career.
Do you have any favorite moments or favorite chips or logic blocks or whatever were designed at your time at TI?
Well, at the time when I worked at TI and ASIC, there were, mobile phones were just starting to become a thing. And we were actually one of the suppliers to Nokia and those early players in the mobile phone network. So, one of the things that I was, again, going back to some of the intro comments, is I was designing these chips, helping Nokia design these chips back in the early 90s and just waiting until I could get my hands on these new digital phones that I've been hearing about. And it was so exciting to see something that you were designing 2, 3 years later became a product that revolutionized society. I don't think it's too bold a statement to say that. So that was very interesting. I would also say I learned another lesson in those early days. One of my account bases right out of college was mini computers. You may have remembered people like DEC and Wang and Data General and so forth, right? And those are companies that no longer exist anymore. And because the world went on, PCs were invented, more compute came locally to your desk here. And so, one of the other lessons I learned early on in my life is that tech is incredibly dynamic and things can shift and change very rapidly. Today's leaders could be a follower or even not even around in 5 years' time if you don't really keep your eye on the prize here. You don't really keep your eye focused on what customers are telling you and what the market is telling you and what's technically possible.
You mentioned tech changing so fast, and that's something I've been learning a lot is it the amount of things that we have to be nimble with and adapt for is bonkers. Like I got a cell phone when I was in high school. I grew up and the internet was no, not what it is today, but still very much there. And a lot of my coworkers and people from like your class of engineering had to adapt to that workforce and adapt to that changing technology. What are some tips or advice you have, especially for people like me who are more early mid career, to see the waves of tech and the trends changing? How do you pick out which ones matter, which ones don't, and keep up with those?
Yeah, I mean, that's a great question. When I first got into the semiconductor industry, which was in the mid 80s, the whole semiconductor industry was only $20 billion at the time. And it took like 10 years to add 100 billion, and that happened for the next 3 decades. So we went through the wave of the PCs, the internet, the mobile phones, and all of those added about $100 billion to the semiconductor market. And now we're entering into the age of AI where in the span of 10 years, the market's going to go from maybe 400 billion to like over a trillion. So what used to take a decade is now happening in every 2 years. So that is an extraordinary pace of change. When you think about the semiconductor industry growing $100 billion every other year. And so, what I would encourage to anybody who's early and mid year career is to really keep up with the trends, really do your research, really be flexible in your mindset, really think about what's coming next. Make sure your skills are fresh because that's on you. That's not on the company you work for. That's on you to be able to really make sure your skills are fresh and that you're keeping up to date. I'll tell you something that I tell my team here, right? There's going to be two types of engineers in the future, right? When it comes to AI, people who lean all the way in and adopt AI in their engineering flows every day. And then there's going to be dinosaurs and dodos, right? I say, please don't be a dodo, right? Don't go extinct because the pace of change is so fast right now. we need to really lean in. We need to see every day, how can I use generative AI? How can I use agents to make my job more efficient? So that's the single biggest thing that I would say to anybody. Lean into AI, really lean in, especially over the next decade, and really look for opportunities to map your human ingenuity onto to be accelerated by machine precision. Right? I don't think AI is going to obsolete human ingenuity anytime soon. I think it's going to channel it. It's going to amplify it. It's going to be a force multiplier.
I love that. And I'd love to talk more about how AI will potentially change the future of chip design and semiconductors. But for this portion of the conversation, I'm curious. I've seen so much integration of like digital and RF and analog circuit design and chip design all melding into one skill set. We rarely now have pure digital engineers and pure analog or RF or signal integrity engineers. The skill sets are you got to have them all now. How is that coming into the world of silicon design, and how are hyperscalers working to take these different technologies and make them work together in a pretty like physically hostile data center, rack sort of environment?
There's a lot to unpack with that question, Daniel. That's a great question. And I tell you, the system companies who are getting into chip design, whether it's the hyperscalers or whether it's a mobile phone, people like Apple, or whether it's, the OEMs of the world, like the Teslas in the automotive space, they have a tremendous need and opportunity to differentiate their system by marrying the software driven workflows onto the hardware, and by really understanding those software driven workflows and optimizing the hardware with those workflows in mind, you can have a tremendous impact. So, when you think about it from an engineering perspective, yes, you have to understand analog, you have to understand digital, but you also have to understand how the software architecture impacts your chip design and take that into account. And I can tell you, in today's world, especially when it comes to analog and mixed signal design, it's becoming more and more challenging. You used to just have to take into account what was called RC delays. Now it's RLC with inductors in the mix, where you have to model thermal noise, where you have to model a power grid, which in an individual chip is starting to mimic like you might see in a city. It's becoming very, very complex, and you have to be able to really model thermal conditions on your chip, which is a really big factor right now in the semiconductor industry. So all of these things, the layout complexity is going way up. As Moore's law goes down a few more notches, some devices that were used to be there, like for example, IO devices, are no longer there, and you have to build complex analog circuits out of just core transistors, which is a new level of architectural challenge. So there's many different interconnected factors here, from thermal to power to digital design, maximizing the frequency, to taking into account analog effects in all of your chips.
So you mentioned modeling a couple times. How much does modeling play into your design? How terrible question, but how good are the models? How much of a true digital twin are they versus how much do you just kind of play with the temperature slider and hope for the best?
That is a great question, right? And Synopsys just bought Ansys a few weeks ago, closed the transaction. And Ansys is the leader in simulation and modeling technology. And the combined Synopsys and Ansys, the new Synopsys now, has a market opportunity of selling into about 30 odd billion-dollar TAM. And a big part of that, TAM, is exactly what you said. It's about making accurate models, whether it's a digital twin of the car, whether it's accurately modeling thermal, whether it's accurately modeling inductance, whether it's accurately modeling the process variations on such complex processes. This is something that the industry has focused an incredible amount of effort on, and we call it MHC, call it model to hardware correlation. And this is a giant focus of the industry. And it's actually taken huge steps forward. even over the last 5 years, because you have to have accurate modeling. Now, you can't model everything with infinite precision, but you can, do a pretty darn good job of really modeling pre-silicon to post-silicon behaviors now.
So how much then? I mean, obviously, you want the IP you design when it gets fabricated and integrated into a bigger design, it has to work. How much overhead do you build into this model? How robust does it have to be something that's marketable to people wanting to implement it?
That's a great question. Like I was just talking to a hyperscaler the other day, and I'll give you an example. Like in the PCI Express, a very common way to interconnect chips into a system. The PCIe SIG, the standards body that defines that, says the channel needs to be 32 dB. It needs to have a certain bit error rate. But when we go talk to our hyperscaler customers, they go, yeah, John, the standard is nice, but I need something that's literally 2 orders of magnitude, better than the standard in terms of the bit error rate to take into account noisy links. Right? I don't need a 32 dB channel. I need a 37 dB channel because I need margin in my data center because I have, what do they call it? The 6 nines, I think, or the 5 nines, 99.999% uptime. And so to design in quality and robustness and performance margins is absolutely critical. And this is something where, hyperscalers in particular are really leaning on IP providers like Synopsys to design above and beyond the specifications to really work in that data center environment.
So to get that sort of margin increase, you clearly must be kind of in lockstep with them as they're developing their systems. What does that sort of relationship look like before you even have, a SKU and you're like, here's our, memory block. How much are you working with them to define what your actual parameters are?
If I go back into the ancient days of IP, which is maybe 15 years ago, right? We used to design IP when the process was quote unquote stable, like a zero point 0.9 PDK, so almost fully baked. And we used to design IP when the standard was fully baked at version 1.0. But now this is the exact opposite of what is happening today. Today we're designing IP on processes as they're being developed. It's not at all unusual for us to be starting with a zero point 0.1 PDK, which is an early view of the manufacturing process. And at the same time, it's not unusual for us, especially with the hyperscalers, to be designing 12 months or more in advance of when that spec is going to show up because they're market makers, they're market influencers. They can drive the entire ecosystem saying, this is what I want to see in the standards. And they want us along with that journey. They want us to be there as the second the standard is ratified. They want us to be there with them to have the IP that's fully compliant and manufacturable.
I'm curious about your relationship with foundries. I just saw you collaborated with Intel Foundry on their 18 angstrom process. How much does process play a part in what you choose to design in the future?
At Synopsys' IP business, we have by far the broadest portfolio of IP on the most number of manufacturing nodes. Our industry, those are called fabs. These are things like TSMC, Intel, Samsung, Rapidus, Global Foundries, to name of the few of the players. And as the IP provider with by far the largest portfolio of what we call hard IP or fab specific IP, we are actually designing with the fabs, we're actually co-designing their processes with them in something we call DTCO, Design Technology Co-Optimization. So before they release a single design kit out into the world for designers to start to use, we, Synopsys, are working with them with our IP to validate, yes, this process is going to be manufacturable, it's going to be high performance, it's going to hit the power targets that the market has. So really, even before the basic process is released, Synopsys is engaged with all of these major foundries.
So it sounds like there's really a tightrope that you have to walk between the foundries and the fabs and the designers who are sending their chips to these fabs to be built. Are there any moments in the last 10 or 20 years where you feel like you were really proud of walking that tightrope perfectly? And are there any moments where it's like, well, we thought it was going this way, but the industry then flipped the script on its head and went a different direction? Can you share any stories, kind of war stories from from between the fab and the designers?
Yeah, sure. Especially playing back over time because I've been in the IP industry here for 20 years. And, we've had at least three major shifts during that time. We went from what's called planar transistors. We went into the area of FinFET, so vertical transistors, and now we're into the era of gate all around transistors. And each one of these transitions, which has been a huge shift over the last 10 years, has interjected a lot of complexity into the design process. And as an IP provider, one of the things that I needed to do in my most of my role for most of my career is I needed to guess right which one of these manufacturing processes would be most successful? What variant of it would be most successful? Because at any given node, like at 16 nanometer or 7 nanometer, there's typically multiple different flavors. And we had to guess which one would be right, which ones our customers would use. And that really involved a lot of market intelligence. It involved a lot of conversation with the customers, a lot of conversations with the fabs. And we mostly got that right. We mostly got that right. But there were occasional nodes, like a 10 nanometer node, that the industry, largely skipped over, and we built some IP for. So at the end of the day, that was kind of a wasted investment. But in general, given our tight ties with both the customers and with the foundries, we've navigated that tightrope pretty well.
Clearly, you have. That's been very successful for you. Another thing I've been kind of thinking through as preparing for this conversation, what is the difference between designing for IP and designing an actual chip from like an engineering mindset?
Yeah, that's a really good question because there is a fundamental shift. When you're designing a chip, you have a very specific application and use case in mind, right? And you design the chip for that specific application and that specific use case. When you design IP, you have to design IP that works in many different applications across many different foundries and across many different use cases. So we have to, in some sense, you could think of it as over designing the IP per se, but it's really making the IP extremely robust to be able to work in many, many different, application spaces. Now, ultimately, that's a good thing because as the customers evolve their own internal designs from, to design, or even as they add features in the design, they can trust in people like Synopsys that we see such a wide range of applications engaged with such a wide range of customers that when they need that next feature, we'll have already designed it into the product and verified it and proven it in silicon, which is critical.
How much are you seeing people take IP and just slap it on a chiplet and call it good to go versus integrating into a larger kind of, monolithic IC?
Another great question, and it's the era of multi-die systems is upon us. Where you have a collection of chiplets put together in a very advanced package, and that's particularly true in what we call the high-performance compute market or the data center market, where more than 50% of the designs today are composed of multiple chiplets, put together, and this opens up a whole new paradigm of from an EDA perspective and an IP perspective. And it's really quite challenging and also quite interesting because the fundamental ways our customers are designing these new systems made up of multiple chiplets is changing, right? They might put like the IO die in 5 nanometer and the compute die in 2 nanometer, and then they have to connect those with very high speed interfaces. And so we're working really, really closely with both the industry as well as our customers to take advantage of that. Now, to go back to your original question and like how often do you see just like some IP, put into like with a little bit of glue logic into a chiplet and ship that? Generally speaking, most die-to-die or multi-die systems today are what we call proprietary. In other words, they're designed by a hyperscaler or a mobile phone person or an OEM that controls both sides of the wire. What you're describing will happen is something called the open chiplet ecosystem. It's where you can buy like a chunk of a design from vendor A, another section of the design from vendor B, and stitch those together into a package. That's in the very, very early days and has that open chiplet marketplace, that ability to mix and match chiplets that weren't designed with one system in mind, is challenging both from an economic standpoint as well as a technical standpoint. So while we're well into the era of multi-die chiplet-based systems, and that's going to continue to explode, we're just scratching the surface of the open chiplet market for, like I said, both business and technical reasons.
And that makes sense, right? The point of a chip is to do something hyper specific and very purpose built. So to go back to throw a bunch of, like 1980s, board designs with just rows and rows of chips, that's maybe, doesn't make sense as you scale down to a chiplet level. What are some of the changes in thinking you've had to approach as chiplets have become more and more of a thing? Does it change for you, or is it still because there's the proprietary kind of glue logic around it, it hasn't changed much?
Oh, it absolutely has changed really significantly and in very meaningful ways. So first of all, historically the IP market used to be, basic building blocks, something like, let's go back to our USB example, the physical layer that interfaces with the outside world and the controller. Now, what our customers are asking for is not just a simple controller in PHY. They're asking for a complex subsystems with many different protocols all put together. And they're actually even looking higher up than that. They're looking for like an IO disaggregation die, where maybe you have a high-speed Ethernet coming in one side and PCI Express going out the other side. They're looking for us as an IP vendor, not just to build those building blocks, but to step up into complex subsystems, step up into chiplets. And that's clearly the next wave for the IP industry, providing more advanced functionality, larger sections of the designs that our customer can integrate. So that's one answer to your question. I think another answer is actually really interesting technically. In the area of 3D IC, when you're stacking one die on top of the next die, that actually has a profound impact on IP, because now what you need to do is you need to make sure that in your IP, you have the ability to route both signal and ground from one top die to the bottom die. And you need to do that in a way where you're not disturbing the circuitry of the IP. So, for example, in a high speed physical design, you want to make sure you're not, having noise coupling into your IP. So, we work really closely with our lead customers on 3D enabled IP to make sure that they can route power and signals through our IP rather than around the IP, which has been the traditional paradigm. And we can do that and still have a robust production worthy design.
So do you see a future where there are, much like there were like standard chip packaging footprints, do you see that for chiplets also, or for 3D silicon also, where we always know the top right is power and the bottom left has a ground trace going through it? Or what might that look like? How do you actually make that work in
We are
reality?
in the early days of sorting that out, and that is a great question because I think in order to have a third party chiplet marketplace take off, that's one of the many things that we're going to have to solve, right? We're going to have, let's say, quadrants of the package with, thermal and physical footprints here that you have to design a chiplet into. And very early days on that, very early days. But I think, some combination of a new level of modeling with some rules-based heuristics is going to be the way to make that successful, but very early days.
So we almost need a new standards body for 3D silicon, like an open chip standards body.
We actually really do. And right now, many of the foundries are leading that charge themselves with their own proprietary that they're now standards that they're now opening up into the industry. And that is absolutely going to be a key way to describe those components, model those components, and connect them together. That is absolutely going to be essential for, true 3D packaging to take off.
It's such a funny concept to me because it sounds so simple in concepts. Like, well, why not just stack a bunch of them together? But the engineering challenge behind that is, you know, arguably on par with any other technology that's blooming today. What sorts of mindsets and approaches do you think will make people successful in the 3D silicon world?
I think the single biggest challenge you hear universally from our customers is the thermal management because you're stacking an enormous number of chips in a small area, dissipating huge amount of power. So how do you successfully distribute that power, that thermal distribution, without creating hot spots into the die that can yield performance problems or can yield much more significant problems? It can result in things like cracking of the package, delamination of the package, if you're not modeling the thermal characteristics well, right? So this is by far the single biggest challenge moving into 3D IC is how do you manage the thermal characteristics very well? And going back to an earlier comment, one of the benefits of the Ansys acquisition is they have the leading platform for thermal modeling inside a package and inside a chip. And we've had an 8-year cooperation with them prior to the acquisition. And now what you're going to see in probably less than a year, first half of 2026, is you're going to see a new level of integration between the Synopsys classic tools and the Ansys tools to really address this specific problem and other similar ones to it.
Can you kind of paint me a vision for what that partnership has been and what it could be in the future, obviously without revealing any yet to be released IP, but what does that handoff or trade-off or integration look like more practically?
Yeah, we have a tool at Synopsys called 3DIC Compiler, and it's what we call the cockpit for doing 3D design, right? So, and that enables you to do architectural analysis, it enables you to do power analysis, it enables you to do thermal analysis. And what we're going to be doing is taking the engines from various other Synopsys and now Ansys tools and plugging them into that cockpit. So you have, as a user, you have one integrated view of all the different aspects of your 3D IC, whether it's power, whether it's performance, whether it's how does your architecture scale. All of those things will be, modeled into a very comprehensive system. And I think that's what the industry desperately needs because today, what we're doing is we're doing that using, it's definitely improving, but using, early versions of that fully integrated solution here. And that's where I think we're going to be investing a lot of time and energy into an integrated solution that allows you to visualize the design from multiple dimensions.
This, I think, sets us up really well for the conversation of, what is the role of AI in the future of chip design?
AI is not only changing what we design, it's changing fundamentally how we design. So everybody knows about the pace of change in the data center, where everywhere the pace is shifting to a 1 year type of cycles in the major chips here, where everybody understands how fast that is moving on that side and how complex those chips are. The biggest chip you can get right now is around 800 millimeters squared. That's how you can manufacture it. I'm talking to some, lead hyperscalers that want to put 10 times that amount of silicon into one package, for their next generation AI applications. So it's absolutely incredible to think about how do you model that? How do you model that from every angle, from architecture, from software bring up? How do you verify it? Thermal management, all of those things are incredibly, complex, right? So it's, AI is not just changing, what we're designing, but it's also changing how we're designing. And at Synopsys, we really believe that you're going to see in the next 18 months a dramatic re-engineering of the engineering workflows. Truly. I mean, they're going to be ripped up and thrown out. You're going to take your design flows today, you're going to take them and drill them not down to the studs, you're going to take and drain that down to the foundations. And you're going to rebuild your entire design flow in this era of agentic AI. Today, agentic AI really means generative AI kind of assistance, but that's only the first step on a 5-step journey. You're going to see other areas where you can apply agentic AI. So, for example, to fix signal integrity, for example, to fix DRC, you're going to have a multitude of agents working together to do a complex clock tree. You know, eventually in the future, you're going to be on autopilot mode where you're going to be able to take a collection of agents and say, hey, design this subblock for me and come back and tell me when you're done. Right. So it's really going to fundamentally change and augment human engineers going into the future. And that's going to be, again, it's really going to require you as an engineering manager to fundamentally rethink how you do design flows.
You mentioned a 5-step, you know, process or plan. Can you talk me through how you see the different levels of agentic AI playing into chip design?
Sure, we have a model that is kind of loosely based on that self-driving car model you've seen from L1 to L5, right? And, like today's cars are mostly L2 or L2 plus. Well, that's kind of the state of the EDA market right now, right? L1 was generative AI, where you're asking the tools for a very, like a chat GPT like response, where you're asking it, hey, how does this command work? Write me a script to do this, right? So that exists today. That L1 capability exists today. We call it knowledge assistance. In the area of L2 designs, that's where you're starting to have a specific agent do a specific task. So a good example of that is, hey, there's a DRC violation, a design rule violation. Go automatically fix that for me. Where you are, as the human, are directing the activity of that particular agent. That's what we call L2. L3 is where you're having a series of agents working together to solve a more complex problem. So, for example, signal integrity. Because to fix signal integrity, you might have to implement a layout change. You might need to re-extract. You might need to re-verify and make sure that, in that whole process, you didn't break things and go back and do it again, right? So that's what we call L3. When you look at something like an L4, that's where you have a collection of agents that are really planning and doing adaptive learning to something as complex as, let's say, a clock tree. Where you are having a very complex clock tree that spans across your whole chip. You have to balance that for power. You have to skew match. You have to do a whole bunch of things that affects almost every aspect of the flow. And then, eventually we'll get to L5, where again, you'll be able to take like a block and feed it into the tools and really, tell it to do that under human, direction, but autonomously done by the tools. So today, arguably we're in the L2 phase, just like L2 plus phase, like kind of like the car industry is as well. But this is something over the next 3 to 5 years. And I think I'm probably being conservative with that projection. I think it's going to be faster than that. You're going to see these workflows dramatically change.
Today, we have lane assistance or adaptive cruise control, but going forward, we're just gonna take the analogy all the way through. We'll have full self-driving that actually actually works.
Right,
um,
exactly.
Much like driving, a lot of people are like, "Oh, I like driving," or a human driver is always going to be better than an autonomous driver. How much skill and experience plays into a state 5 years from now, where if I can just design my inputs and my outputs and say, here's what I want you to do, give me a chip, where is engineering expertise still required and still valuable?
That is a great question. And it's something that I think is really critical, because the way I look at it is, this is where human creativity and human ingenuity gets amplified by machine agents, not replaced, but amplified, right? I mean, who's going to come up with that architecture? Who's going to model the software framework? Who's going to think about the complex interactions between the hardware and the software and the application mode? Who's going to be the conductor in this orchestra of agents, right? These are all areas where human engineers are not going to be, replaced anytime soon. Instead, I really look at it as the AI agents augmenting human ingenuity and amplifying it and unleashing it. And I think you're going to see a whole new wave of creative ideas, that are just going to be, I mean, they're just going to be mind blowing. I can't wait to see what the future is going to look like in 10 years.
Yeah, no, I see that for sure, and am excited for that as well. I think accessibility to technology, I think always, you know, in the large scale is really good for humanity and good for technology, and it opens up things that we could never have predicted, except for science fiction authors. Um,
Exactly. Yes.
when it comes to gaining that expertise, this is something I'm concerned about for our 20-year view is at some point AI could take the place of entry level junior engineers who have done that iteration and that kind of less glamorous work to gain those sorts of intuitions and experience. How does someone coming out of engineering school in say 2030 or 2035 gain that sort of experience that AI is now able to do routing of clock trees and look at timing diagrams and all that?
This is a great question. And my youngest daughter is 16, right? And she's interested in the STEM fields and architecture and so forth. And, this is a very active dinner time conversation, right? It's like when you get out and you graduate, and into the workforce 10 years ago, what does that look like? What can AI do and what can not AI do? And what I really encourage her to do is to really think about areas where you're harnessing that human creativity, because I don't think that AI is ever going to be able to, master that same level of creativity. So she's interested in architecture. I tell her to lean into the creative aspects of architecture, not the mechanical aspects, but the creative architecture. And think about that. Think about new ways you can use materials, new ways you can think about achieving design goals for the building. And that's what I really encourage her to do. And what I would encourage any new early career person to do, right, is for lean into AI, and use it to complement and be a force amplifier for you, a force multiplier for you as a new engineer. Don't be afraid to lean into it. The people who are masters of using AI are the people who are going to have long and successful careers over the next couple of decades.
So looking at someone, we fast forward 20 years and we're like, oh, you have had a hugely successful career. The 20-year later version of me is talking to the 20-year later version of you.
Yes.
What sort of skills, what sort of mindsets, what sort of things do you think they will have done to set themselves up for an illustrious multi-decade career?
Well, first of all, I hope the 20-year-old version of you and me are having a nice glass of wine, maybe in the Italian Riviera, and
Sounds great.
enjoying this beautiful earth. But to answer your question in terms of, what does that look like? I think what it looks like is that there's going to be one word that's going to be the key above all other words, and that's adaptability, right? Being open to new ways of doing things and pursuing those new ways. In my own career, I mean, many people at my level have had like a very structured career plan, and I've never had a structured career plan. You know what I've done? I've always said, hey, this is an interesting problem. This is interesting technology. I want to learn about it. When I learn about it, I get passionate about it. When I get passionate about it, I apply my full self to, using technology in creative ways. And with that passion and force, I master it and I add value to the company. And in so doing, I've been able to grow through the ranks. And, from my perspective, pursuing things that interest you, pursuing things that you can be passionate about, pursuing a breadth of knowledge in many different related fields is going to be the absolute key to the next generation success in engineering.
I love that. And this is maybe too philosophical for an engineering podcast and engineering session like this, but one of the things that's I take to heart a lot, research is showing kind of how the brain works in terms of like following your passion. What it turns out is that as humans, when we invest our curiosity and we invest our time to research and work on a thing, we then start to kind of, maybe it's frog in boiling water, but we start to like that and find passion in that thing that we're doing, even if initially we weren't drawn to the, the glamour of that idea. So I love the idea that doubling down on learning and focus while also keeping an open mind is a really, will open up paths that you never thought possible. Especially, case in point for me, how did I end up here? I don't know. But, you never
Yeah,
know where a career will lead. That's for sure.
right, right. But just follow your passions, because if you're passionate at it, you're gonna invest your time in it. You're gonna be successful at it, and that's gonna pay you back. That's what I would say.
So, if we were to recommend some people to start investing their time learning and growing, how much would you say it's time to invest in, learning the ins and outs of like the underworkings of AI versus finding AI tools that are emerging and getting really good at kind of interacting with those?
Today I see job classes like AI prompt engineering, and those are necessary like in the short term, right? But those are not where you need to be focused your energy on. What you need to be focusing your energy and creativity is not on some short-term temporal thing like that, but more opening up your brain, like how can I use these AI technologies to improve my productivity and accomplish my job more efficiently. That's what you need to be focusing at, because at the rate of change of AI, what you learned, it's crazy, even 6 months ago, is starting to become a little bit dated. So, any of those kind of mechanical things you were describing, those are going to be ephemeral, right? What's not going to be ephemeral is the thought process of how do I apply these new capabilities to the job that I have at hand.
I've been hearing a lot about Risk 5 as a technology. Can you dig into what you see from Risk 5 today?
In the area of RISC-V, which is an emerging alternative to the existing processors. Processors, as you know, are like the brain of the computing engine, right? So that's the analogy that I use, right? So you have, of course, the x86 architecture, which has been around for decades and is really efficient in certain workloads. You have ARM, which is just going through many, many different applications, started in mobile but is now taking the data center world by storm as people are designing custom data center chips. And then you have like RISC-V, and RISC-V is an open source compute engine here. And it is something which is at relatively early phases of getting a foothold, because one of the most important things when it comes to processors is it's not about the hardware, it's about the software that runs on that hardware. It's about the ecosystem, it's about the drivers, it's about the applications. And today, when it comes to RISC-V, we're relatively early in that ecosystem development. It is starting to accelerate, and I think RISC-V will have success, over time. But I can tell you, x86 and ARM right now are on a really strong roll, particularly ARM getting into the data center here. They've been investing in that area for more than 10 years now. I think their first investment, memory serves, was like 2013. And it's really, taken them the better part of a decade to really take that investment and have it really propagate out. And they have a very successful architecture here. And while we have, RISC-V based cores that we call ARC-V cores, we make it very clear we don't compete head to head with ARM on those data center chips or on those mobile chips or so forth. We look for applications that are deeply embedded applications, and then that's where the sweet spot is for us in the RISC-V arena, deeply embedded applications.
Kind of the promise of open source and what maybe this is over dramatic, but the kind of the promise of Risk 5 is you can use this open source core and this open source ISA and not have to use and license IP As someone who has built a career on IP, what is your take on open source versus IP, and how do those play together?
I'll take you back to my time when I worked at AMD. At AMD at the time, I was responsible for designing embedded x86 microcontrollers. Now, if you know much about the x86 architecture, which is a complex architecture, it's not the most power optimized for the embedded applications, as compared to ARM, which was designed from the very beginning. But when I was at AMD and I was designing those x86 based microcontrollers, we sold a lot of them. And I learned a very important lesson in my life at that time, which is it's the software, stupid, right? When it comes to processors, it's not about the hardware. I mean, that's important, of course, but it's really about the ecosystem and the software that runs on top of that. That is the core to the success of all processors. And that's where we need to go in RISC-V and put effort in developing that ecosystem more.
So it doesn't matter how good the tech is if you can't use it, it's really not that good at the end of the day.
That's correct. I mean, when I talk to customers, their number one concern about adopting a new processor, it's kind of like a brain transplant, right? They want to know that, all the apps that used to run, are still going to run, onto, their new processors. And that is the number one criteria when companies look at switching processors.
Well, we're approaching the end of our time. I'd like to ask people a couple kind of lightning round, off the cuff questions.
And
First question for you. If you had a magic wand and could change a law of physics or change something about the way technology fundamentally works, what parameter, what thing would you change with that magic wand?
Oh, for me, it'd be easy. It'd be anti-grav because I want to fly everywhere. I just want to
Okay.
put an anti-grav engine on me and just take off and fly over be like a bird. That's what I would say.
Sounds
So
good. I like that a lot. Um, are there any in the history of science fiction as a science fiction connoisseur? Are there any books or movies or concepts that you think really got it right, or any that you think really got it wrong?
yes. So it's very interesting that one of the most influential books in my career was a very popular book called Ender's Game and the sequels from that. And it really examined, many of the concepts of how you apply technology to society and what the impact is. And that's what really fascinates me, right? What's going to happen to basic societal norms if you can live to be 200 in good health? How is that going to change, right? What if you can clone yourself? What are the rights of that clone, right? Do you have clones that go off to work and other clones that go off to garden? How do you reintegrate memories from those clones? I mean, those kind of ideas are just fascinating to me. And so I really enjoy reading the juxtaposition of how technology is going to shape society and how society is going to be shaped by technology. That's what's really interesting to me. You know, ray guns and aliens and space saucers, those are nice and those are fun, but I really like the intercept of technology and society implications.
That was one of the most surprising things about the Ender's Game series of books for me. Is the first one is kind of ray guns and aliens, and then the rest of the series is like very philosophical. It's like a total
Exactly, right.
total left turn. So
Yeah.
um, be warned if you haven't read those. Recommended, but they're different. You've spent time in sales, marketing, and engineering. You were the VP of marketing for a while. As engineers who are looking to work more collaboratively and maybe more open-minded with marketing, what sort of advice or mindsets do you have for those folks?
That's a really easy one because engineers love to talk about features in their products. They love to talk about capabilities. But customers don't buy features. What they do is they buy benefits. So you need to shift your mindset and you need to tell the story of not the speeds and feeds of your product, but you need to tell it from how does this benefit the customer? What problem is this solving for the customer? And that's a leap that many engineers struggle with because they're so passionate about their products and the technical challenges that it took to bring that product to market. But ultimately it's about what problem is this product solving for our customers?
Last question for you. You spent nearly 3 decades at a single company. That is pretty rare these days. What sort of benefits have you found from that? And do you still think that's a viable sort of option for people who are starting out today?
I worked for 3 decades for Synopsys because I was very attracted to the culture of Synopsys, particularly the culture of being very, very high integrity. Also, the culture that values people. Also, the culture that really puts an emphasis on technical greatness. And those are things that it's not about whether it's one company or multiple companies. Those are the kind of primary characteristics that I would say to anybody starting out. It's not about staying in one company or multiple companies. It's like, is this company you're working for innovative? Is it agile? Does it treat its people well? Does it have high integrity? Those are the things that I look for, because with those things, you can make a difference. And I would encourage anybody, if they do stay at a company for a long time, to take many different roles within the company to get a different lens through the many different views. And that's just going to make you a stronger contributor all around.
Well, that's wonderful advice. We're out of time. Thank you so much for being here today, John.
Oh, thank you. It's a real pleasure. Thank you so much.
That was John Koeter, Senior Vice President at Synopsys, and this keynote was brought to you by Breadboard. Breadboard is changing the way engineers design and source. Get 80% faster procurement, up to 20% lower cost, and bombs in minutes, not days, for fewer errors and faster launches. Don't get left behind. Start building smarter at breadboard.com. The All About Circuits Summit series happens each Wednesday in October, and sessions will also be available on demand. Today, live, we're talking all about analog and power, and have sessions exploring transistor technology, power connectors, power for autonomous mobile robots, static protection, and more on IP for ICs and EDA. Each session you sign up for gives you an entry into the giveaway, and make sure to check out the microsites from our presenters to learn more about their topic. Thank you for joining me for today's keynote. I'm your host, Daniel Bogdanoff. I hope you have a great day of learning, and I'll see you back here next Wednesday, where I'll be joined by Ted Carlin from Infineon Technologies to talk about sensing technology and 60 gigahertz radar. I'll see you then.